Good. So let's move right now to the formulation of the finite volume method for the flow problem, which I think might be more interesting for you. And there are some important lessons to be drawn from that. Especially, I think one of the lessons we have already drawn, we're implementing the custom application for oil and gas simulations in the pipes. And this comes down to the fact of how to properly choose location of storing the variables, the pressures and the velocities, which is extremely important, because otherwise you will run into a numerical scheme that is unconditionally unstable, or at least very, very, very often unstable. And let me show you the following problem. Like when we've been discussing the find difference method, what we've been drawing was just a line with nodes. If we're discussing the 1D, and we'll start with the 1D example. If we were discussing the 1D find volume method, please always think about that as having real volumes of some space, but just discretized in one direction. What I mean is, let's think of really having the volumes but simply discretized in one direction. This might be a stupid way of thinking about that, but I think it's not. Mainly because if you want to discretize any diverging or converging geometry, you can still do it with 1D find volumes. But please remember that, for example, this surface area will be different from that surface area, and so on and so on. And you will come up with proper formulation that is like, that still conserves mass, energy, etc., because it's how fine volumes are formulated, coming back to going out from the differential form of the equations, then they really discretize the balances of mass, energy, etc. So if you follow such a procedure, you will be fine, because it's really how physics works. You just have discretized the domain in one direction, not in, let's say, in 2D or 3D. Okay? So that's the first comment. But when we're already covering this example, then let me show the following thing. Let's imagine that we've got a 1D flow case. We already know that typically the variables are represented at the centroids of cells. And let's see what we've got. If we want to discretize the Navier-Stokes problem, this means that, let's assume the steady case. This means that we want to discretize velocity times dv dx equals minus pressure, or maybe divided by density. Well, it's difficult to discretize the friction forces in 1D, because they mainly come from the parabolic distribution in the other direction, not in this direction. So this would be a bit stupid, but let me write like that. And the other thing that we have is the is the requirement that the divergence field must vanish. So what can happen here is just see. In finite volumes, if you just consider the physical intuition, is what would you do? If you need to write the momentum balance for this finite volume, you would be using the velocity, let's say it's the ith. Cell. So the ith velocity, maybe you would do some approximation to this gradient. And, sorry, not the steady case. It will be much more illustrative to show you the unsteady case. Then you've got the acceleration of the increase in the velocity value at this cell. This one will vanish for our 1D case with constant area because the velocity across the channel will be the same. This will not vanish if you would consider, and you can consider, such a case. And obviously, this divergence would translate to something different. It wouldn't mean that dx is equal to 0, because it's not. You would need to come up with the continuity equation for 1D, but this would be valid. Like the continuity equation in the discretized form would be that, let's say, a at the left face times the velocity at the left face, however interpolated, plus a at the right face times the velocity at the right face must be equal to 0. Yeah, it's like the balance of the volumetric flux coming in and coming out of the volume. So after this short comment, let's focus on that case. We can have the most simple case of having constant cross-section of the channel. This one clearly vanishes. Where this one would vanish as well in the 1D case, because if you want to represent the friction forces, you would rather say that they can be represented as some friction coefficient times the velocity, because this should represent the friction against the walls.
Minus, I guess,
yeah.
KV.
Okay. You're the expert in the friction forces in 1D flows. But right now, the most important conclusion is C. How would you typically discretize this one? What you would do in the simple case is physical intuition. What does accelerate flow of this volume of the fluid? Like the pressure difference between this interface and this interface. So what you would do physically to account for the pressure difference is you would write, okay, I should take this pressure and this pressure to calculate how large is the pressure difference that accelerates this fluid element to the right side. Fine enough, but what you would do for the neighboring cell, you would follow the same procedure, and you would say, okay, let's take this one and that one, and now let's see what kind of erroneous field we could get that would still fulfill our equations. The problem is that we could draw the pressure field like that. Okay, and now see, if we were considering this fluid element, we're taking the pressure difference between that and that cell, this 2-1. What's the gradient? 0. Okay, we're doing it for that one. What's the gradient? 0. And so on and so on. So for each cell, you've got 0 gradient, and you've got no flow acceleration, but completely stupid pressure field. And this one satisfies your discretization. So that's the real problem. The problem is that you can have, you can generate such a checkerboard pressure field, and it's really how people call it. Checkerboard pressure. Well, obviously it doesn't matter how large the difference in the value is. So this means that generally your discretization, the matrix that would come out from such a discretization, is a singular matrix. You've got infinite many correct solutions to the problem. Whatever similar pressure pattern you generate, this will satisfy your equations, and it will induce no flow whatsoever. So you've got singularity in your problem. The problem is not well defined, which means that the algorithm is not okay. Yeah, okay. Let's start with the question.
But on the boundaries, we wouldn't have a 0 gradient. So why maybe wouldn't that help to generate a flow?
Well, not necessarily, because typically on the inflow boundary you would specify the velocity, and we could say, all right, so we already have constant velocity along the channel, and we're trying to calculate the increase of the velocity, and it means that, well, you have got or you haven't got the acceleration, still you've got ambiguity in determining the pressure.
Yeah, like if you had the velocity inlet and pressure outlet, you would have constant pressure on half of the cells. Then it's, at least it's constant on half of them, but it's still unbounded on the rest of the cells, I think.
Yes, exactly. Like you can quickly generate numerical instability in your solution procedure. Like either any perturbation arises, then it can quickly grow without any limitations.
And if does this problem appears also if we reformulate our equation to a Poisson equation for pressure?
No, probably not. But I think you can only generate the Poisson pressure equation if you're dealing with the unsteady case. At least for finite elements, I think you only for the unsteady case have got the proof that something like that resolves the unsteady Navier-Stokes equation. Anyway, generally in classical fine volume method, you do not apply the pressure Poisson equation. You start with the Navier-Stokes formulation, and I will discuss some details of that later on.
Okay, so maybe I was wrong.
Go ahead.
I thought that basically simple method is like formulating a Poisson equation. Like it's close to that. So
a bit yes, but partly the simple algorithm is just way of solving the linear system of equations, nothing else. So once you've come up with the discretization of the physical problem, and you and you finished with the discretized matrix, then it's already end of the numerical scheme. The rest part, what you're doing is you're only solving the system of linear equations that you already have. So if you got any problem with your discretization scheme, the problem is already present in your matrix. That one, the checkerboard pressure pattern, and the problem with storing the pressure and velocity variables at the same locations is the most important thing to be remembered for Navier-Stokes equations and the fine volume discretization. How can you get rid of this problem?
You can translate point of storing pressure, for example.
Mm-hmm. Exactly. Typically, what is done, typically we are saying that we will store pressures here at the centroids, but what we would do is we would transfer the point where we are storing the velocity variables to the interfaces. Well, then it turns out that if you want to have the inflow boundary condition, you already have some velocity value exactly at the inlet, which is nice for implementation of the inflow boundary condition. Then if you want to discretize the Navier-Stokes equation, then what you're using is you're drawing such fine volumes for velocity discretization, and then pressure variables are directly accessible at the interfaces of these fine volumes, and you get rid of this problem. So it's already properly defined. Yeah, and you store the pressures at the other locations, at the centroids of the original cells, and that's it. Probably not much more to.
So it's like we have two meshes, like the pressure mesh and the dual.
So to say. And this approach is called the staggered grid. Staggered grid. You will find much information in the literature. This concept can also be applied for 2D or 3D. Just imagine that we've got such a geometry. And we are interested in computing flow in a square domain. Again, you would have the pressure variables at the centroids of cells. Then you're storing the x components of velocity at these interfaces, and you're storing the y components of velocity at these faces. If you want to discretize the Navier-Stokes equations, then when you're discretizing the scalar momentum equation for the x velocity component, then you need to imagine such a fine volume. When you're writing the equations for the y velocity component, you need to imagine such a fine volume. Well, and basically that's it. You still need to to discretize this constraint. But what you do is, well, that's extremely simple in the staggered grid approach. Why is it extremely simple?
You can just sum up the product of phase, area, and velocity.
Exactly, because just see, you already have got the velocities at the interfaces, and divergence, the vanishing divergence of the velocity field means simply the equilibrium of mass in the given fine volume, and your perfect fine volume to represent this solution is this one. Inflowing flux, outgoing flux, incoming flux, outgoing flux. And that's it. Good. Questions to that? You will probably not be implementing a fine volume method in 2D or 3D very, very often, but this might happen not once that you will be implementing fine volume method, at least in 1D. We did it already a couple of times, and it seems to be a very, very simple discretization method. But if you want to develop some custom applications and really quick models, like writing the fine volume, 1D fine volume method for the flow, coupling with many different heat transfer correlations, etc., friction coefficients, like can make a really very accurate algorithm that is extremely simple and it can be solved extremely quickly. So, as said, probably you will not implement the 2D or 3D case too often.
Actually, like on our company repository, there is a finite volume library for 1D. We make it with our former colleague Shinka.
Okay, so you already know that we've got the repository for 1D fine volumes if you need it for any of your future projects. Still, quite many problems can arise if you've got rapid changes in the flow velocity, or you've got some transported quantities that you transport from one cell to the other. I will want to mention the topic of limiters, but let's mention the limiters in one of the last lectures, not right now.
Are we going also to cover another approach with the Riccio interpolation?
With what interpolation?
Riccio, I don't know if I pronounce it correctly. With the one that the velocity is stored in the same node that pressure. But
that would be perfect if you can prepare yourself to say a couple of words about that.
Okay, so maybe later.
So maybe later. Yes, because just see, the staggered grid approach is very nice if you're dealing with, well, very structured geometries. If you want to implement fine volumes on the unstructured meshes, like, it's really difficult to imagine that you will be dealing with triangles storing pressure somewhere, and well, even not accent y velocities, well, how should you do that? But maybe this will be your topic.
Okay, I can prepare for that.
I think you need to exploit some gradients to make it stable, right?
Yeah, like it uses the pressure gradients at the faces. And actually, like this is the formulation that is used in Fluent, and like for sure it's in OpenFlow, but I don't know if OpenFlow, like maybe it's also available for using the staggered grid option. I don't know.
No, I don't think the commercial codes use the staggered grid approach. Simply because commercial codes or general purpose codes are implemented to work on unstructured meshes. And even if you import a structured mesh, then it's still handled as an unstructured mesh.
Yeah, but as far as I remember, the CFX is working on staggered approach, or
I don't know the details of CFX, but I mentioned yesterday that we are discussing the cell-centered fine volume, but there is also the formulation vertex-centered fine volume, which, to be honest, I don't know exactly, and I have never worked with that. But then in the vertex-centered fine volume, generally the variables are stored at the vertices of the fine volumes.